Hi, in this video we're going to look at rounding of floats. So we have the round function, which is available in Python. It's built in, you don't have to import it from the math library or anything. And it takes in one parameter at least, mandatory, which is the number we want to round, and then another parameter n that defaults to 0 that specifies, the multiples of 10 that we want to round to. So we'll wrap our heads around what that means exactly. It's actually pretty straightforward. So you might think of it, if you see round 1.23 comma 1, as you're rounding the number to one digit after the decimal point. And that's correct, that's true. But n can also be negative. And so it's not really just number of digits after the decimal point that we can round to, it's number of digits before the decimal point. And in fact, what it means is that we are rounding to multiples of powers of 10, be they negative or positive. And we'll take a look at that in some detail. So the round function is the last way that we looked at of coercing floats to integers. So remember, we had truncation, we had ceiling, we have floor, and now we also have round. And so we can use any of those methods to coerce a floating point number or a non-integer number to an integer number, an integral number. So one thing to point out, if n is not specified, it defaults to 0. And so when we round with just the number, but no n, we'll get an integer back. We're going to round to a power of 10 to the negative 0, which is 1, right? 10 to the 0 is 1. So we're going to round to a multiple of 1, which are the integers, right? Integers are all multiples of 1. So when we do that, the round function will actually return an int data type. So if we call round x for any valid or acceptable number here, we'll get an int back. However, if you actually specify n, then you'll get the same type that you used to call in. So if x was a float, we'll get a float back. If x was an int, we'll get an int back. Of course, you probably wouldn't pass in an int with an n that's positive. It doesn't make sense. But you might want to pass an int with a negative number n, right? And we'll see examples of that later, what that means. Now, it also does mean that if you call round x comma 0, we've actually specified n in this case, even though it's going to round x to an integral number, in other words, to a whole number, it will be the same type that was passed in. So if you use the float, you'll get a float back. So if you round 1.23, you'll get 1 back, which is the integer 1. If you round 1.23 comma 0, you'll get 1.0 or 1 as a float back. Small distinction, and usually again in Python we don't really care that much about the data types. Everything just works, and we don't have to, unlike other languages, have static typing, so that's why we don't have to worry about it too much. But it's there just in case you need to know. So let's look at an example. Let's start with n equal to 0, which means what? We're looking at the closest multiple of 10 to the negative n, 10 to the negative 0, which is 1. So we're looking at the closest multiples of 1. What are multiples of 1? 1, 2, 3, 4, 5, 6, 0, negative 1, negative 2, negative 3, and so on. It's all the integers. So in fact, what we're going to do is look at this on a number line. Much easier to see what's happening there. So the two contenders that we have are 1 and 2. They are multiples of 1, and they're the two numbers that are around 1.23. So 1.23 sits in this interval 1 to 2. And to round, we therefore have to find the closest one. So we have to look at the distance between x and those two, and we find that the closest one is 1. So when we call round 1.23, we'll get 1. Okay, so pretty straightforward, nothing very fancy here. It's called rounding to the closest. But the closest what? Multiple of powers of 10. So for this case, n equal to 0, we're looking to go to the closest multiples of 1. Now we can look at n greater than 0. Let's look at n equals 1. So we're rounding to the closest multiple of 10 to the negative 1, which is 0.1. So we're going to look at multiples of 0.1. What are multiples of 0.1? Well, 0, 0.1, 0.2, 0.3, and on the negative side, negative 0.1, negative 0.2, negative 0.3, and so forth. Again, let's just look at a number line. So if we look at x equals 1.23, then the two numbers that are going to be contenders for this are 1.2 and 1.3, multiples of 0.1. Again, we have to look at the distance. And again, as we can see, 1.23 is closer to 1.2. And so therefore, the round of 1.23, 1 will give us 1.2 back. So now let's look at negative numbers. It works just as easily. So n equals negative 1. Now remember, we're looking at closest multiples of 10 to the negative n. So that means 10 to the negative negative 1, which is 10 to the 1, which is just 10. So when we specify n equals negative 1, we're rounding to the closest multiples of 10. If we had n equal to negative 2, we'd be rounding to the closest multiples of 100. If we had n equal to negative 3, closest multiples of 1,000, and so on. So this n is very flexible, right? It allows us to work both ways. So let's take a look at 18.2, and we're going to want to round to the closest multiple of 10. So again, on a number line, what are the two contenders? 10 and 20, right? These are both multiples of 10, and 18.2 sits right between them. Again, we have to look at the closest one. So we look at the distances, and we find that 20 is the closest. So round of 18.2, negative 1 will return 20. Right? It's the closest number. And you can work with higher values of n in the negative direction as well. Now, one thing I didn't talk about are ties. Ties is what really causes some of the issues with this. The closest, that's easy. But look at this example here. Let's look at x equals 1.25, and let's assume we're working with multiples of 0.1, so an n equal to 1. Then the two contenders are 1.2 and 1.3. What's the distance? Well, 0.05, 0.05. It's the same distance. So what's the round equal to? Right? We don't have a closest value. There is no closest value. So we need a tiebreaker. We need to figure out, we need to decide, well, which one are we going to pick? Now, typically, we would expect 1.25 to round to 1.3. That's kind of what, we've grown up with, what we learned in school, and we just always round up, right? That's called rounding up. Now, a better terminology than rounding up is called rounding away from 0. Because if you round 1.25 up to 1.3, you've moved just a little bit away from 0, right? So we're rounding away from 0. And the reason why it's a better terminology becomes more apparent when we look at negative numbers. Yes, those pesky negative numbers. They always cause problems. So if we have round of negative 1.25, 1, we would expect the result to be negative 1.3. In other words, we've rounded down. We've rounded away from 0, right? We were at negative 1.25, and we've now moved a slight step away from there, right? Slight step away from 0 down to negative 1.3. So instead of saying we're rounding up for positives, we're rounding down for negatives, we can just say we're rounding away from 0. That's why it's a better terminology. It's consistent between those two. So this type of rounding is called rounding to nearest. That's how we round. And then we have to specify the tiebreaker with ties away from 0. So that's a standard way of rounding, the one that we're just used to. However, here's what happens if you write this in Python. Round 1.25, 1. And Python is not the only language that does that. Many others do it as well. If we round 1.25 to 1 decimal point, n equals to 1, we don't get 1.3 back. We get 1.2 back. It's like, oh, so it's rounding down, right? So it rounded towards 0, not away from 0. What's going on? Well, how about round 1.35? Well, that's 1.4. That rounded away from 0. What's going on? It doesn't seem very consistent. Away from 0, towards 0, right? This one, yeah, okay, that's what we would do, but this 1.2, well, we expected 1.3. And the same thing happens with negative numbers. If you look at negative 1.25, you get negative 1.2, which was towards 0, and negative 1.35, you get negative 1.4, which is away from 0 as well. So something's going on here. It's not the standard rounding algorithm. And that's why I said ties can be pesky, because you have different ways of determining and defining how you deal with ties. Everything is going to the closest value. So if you don't have a tie, then the round works just as expected. But when you have a tie is when you have a problem. So what's going on? Well, let's look at something called banker's rounding. That's kind of the common term for what we just saw. And it's basically specified in the IEEE 754 standard. You can go look it up if you want. But essentially, here's how it works. It rounds to the nearest value. So it's the regular, closest value. But for ties, they're rounded to the nearest value, which have an even least significant digit. So what does that mean? Let's look at an example. That's the easiest way to understand what's going on here. So here we have 1.25, and we're using an n of 1 again, which means the two contenders are 1.2 and 1.3. So we need to find the closest one. Now in this case, we have a tie. And so what we do is we look at the least significant digit, which in this case here is 2, and this case here is 3. And we round then to the one that's even. So in this case, 2 is even, 3 is odd, right? So 2 is even, which means that when we round 1.25 comma 1, we're going to return 1.2. If we look at x equals to 1.35, then 1.35 sits between 1.3 and 1.4. Again, it's equidistant, so we have a tie. And the least significant digit 4 here is even, 3 is odd. So since 4 is even, right, we only looked at the least significant digit, 4 is even, which means that we're going to pick 1.4 for the round. And in fact, that's what it returns. It returns 1.4. So this is called banker's rounding. Now, why do we do that? Why not just use the round away from 0 the way that we're kind of used to? Let's look at an example with n equal to -1. So we round to the closest multiple of 10 to the -1, which is 10, right? So we're going to round to the closest multiple of 10. So let's take a look at x equal to 15. And on the number line, it means that we want to, the two contenders are 10 and 20. Again, the distance is equidistant. We have 5, right? So we have a tie. So how do we define the tie? We look at the least significant digit. The least significant digit here is 1. Here it's 2. The zeros don't count. Remember that. Leading, trailing zeros don't count. So 2 is even. So 20 is going to be our choice. And so when we round 15 with a -1, for n, we get 20 back. On the other hand, if we do 25, which sits between 20 and 30, the distance is also 5. It's equidistant. And we have a tie. The 2 here, the 20, right? The least significant digit 2 in the 20 is even. The 3 in here is odd. So we pick the even one. We'll always have one even, one odd. So we do that, and therefore we'll return 20 as well. So that's kind of surprising. If we round 15, we'll get 20. If we round 25, we'll also get 20. So it's kind of sometimes we round away from 0, sometimes we round towards 0. Okay, it's kind of going to be hopefully evenly spread since we're picking the even one and we always have either even or odd, digits. Now, why do that? Why do bankers rounding? Well, it's less biased than always taking ties away from 0. And consider this. Let's say we're averaging 3 numbers. And this really comes into play when you're, let's say, doing a lot of computations with numbers, and banks do that, right? They add up amounts, maybe they calculate interest rates, and they need to round to, let's say, 2 digits after the decimal point. And if each time they round, and let's say that, your interest you earned for that month rounds, and let's say you were at 1.25, then you're going to actually get rounded to 1.3, well, if that's 1 digit, let's say they round to 1 digit. 1.25 is going to round to 1.3. 1.35 is going to round to 1.4. Well, each time they're giving you that, 0.05 extra bit of interest that you didn't actually earn when you're at ties, right? When you're on ties. And so what happens is that if you have billions of transactions, well, that decimal dust builds up pretty quick. In fact, that's how some people think that they can skim from banks, right? You basically kind of, skim off the decimal dust after rounding, and you can make a lot of money because you have a lot of transactions. So that's the problem with rounding away from 0, is that, you kind of have this bias where if you're dealing just with positive numbers and you're always rounding away from 0 and you add that up, you're starting to move, further and further away from the true addition. So we can look at that in a more simplistic way. by looking at these three numbers. And let's say we want to average these three numbers. So if we average them, well, the sum is 4.5 divided by 3, so the average is 1.5. Now let's say that we want to find the, we're going to round first and then average. Let's see what happens. So using standard rounding, 0.5 would become 1, 1.5 would be 2, 2.5 would be 3. If we find that average, we get 6 divided by 3, which is 2. On the other hand, if we use Banker's rounding, 0.5 will round to 0, 1.5 will round to 2, and 2.5 will also round to 2, right? Every time we're rounding to the even. So now if we take a look at the average, this sum divided by 3 is 1.3 recurring, which is a little closer to 1.5 than 2 was. So this is what we mean by it's less biased than always moving away from 0. And in certain cases, banking for example, it's really, really important that you consider those kinds of problems. You know, in finance as well, you want to be careful. And even in numerical computations, you want to be careful that, you know, your rounding errors don't accumulate too much. And so if you have a biased way of rounding, then you're going to further exacerbate the rounding errors and the rounding issues. So Banker's rounding is a pretty good way of getting rid of that bias. It doesn't necessarily get rid of it, but at least it tries to get rid of it. Now, if you really insist on rounding away from 0, well, that's not built into Python, right? Your round is using Banker's rounding. So what can we do? Well, a common way that comes up on the internet, you'll find is this. They'll say, oh, just take x plus 0.5 and then truncate it, right? And that kind of works. 10.3, if you take the int of 10.3 plus 0.5, you get int of 10.8, which is 10, right? So we just rounded 10.3 to 10. If we take 10.9, well, 10.9 plus 0.5 adds up to 11.4. If we take the truncation of that, we get 11. So 10.9 was rounded to 11. That kind of works. 10.5, right? We get 10.5 plus 0.5, which is 11. We truncate that, we get 11. Well, that kind of works too. 10.5 rounded up to 11. So we're good. Now, there are a couple of problems with this, however. One is that this is only really valid for rounding to integers, right? But if you want other powers of 10, you'd have a more complicated way of doing this. The other thing too is that it doesn't work for negative numbers. And very often people forget about negative numbers. And if you're dealing with values that you know are always going to be positive, then this might work for you. And if you're trying to find a quick way of doing this round away from 0 for positive numbers and you're rounding to integers, by all means, this works fine. This is great. However, if numbers could be negative, you'll run into a problem. That's not going to work. Let's look at negative 10.3. If we're rounding away from 0, we should expect to get negative 10. But if we look at the int of negative 10.3 plus 0.5, which is what this formula was, we get int of negative 9.8, which is negative 9, not what we expected. So it doesn't work. And negative 10.9, that will actually round to negative 10. Again, not what we expected, not what we want. The problem here is that we needed to switch. For a negative number, this needed to switch to a negative 0.5 and a minus 0.5. Then it would work. But now we have this thing of, well, if x is positive, then add 0.5. If x is negative, subtract 0.5 and then truncate, right? So you have to be careful. It's not quite straightforward enough. And then the negative 10.5 also rounds to negative 10. So same problem there. So this is an acceptable rounding method. That's fine. This is called rounding towards plus infinity. In other words, we always round up, right? Even with negative numbers, we'll round up. But of course, we still have to be careful, right? We have problems here. So rounding towards plus infinity is fine. That is an acceptable way of rounding. And when we get to the section on decimals, we'll take a look at that as well in more detail, because all these rounding mechanisms are actually implemented in the decimal library when you deal with decimal numbers. They are not, however, implemented in the floats. So this works, but it's not rounding towards 0. Okay. So if you really insist on rounding away from 0, let's see how we could do it. So here's how we want to think about it. We first want to strip the sign of x away. Forget about the sign. Forget about whether it's negative or positive. So take the absolute value of x, add 0.5 to it, and then truncate it. So basically what we had before in the last slide, except that we have to take the absolute value of x. And then, after we have that result, put back the sign. Now what's the sign of x? Sign of x is simply a little function that returns 1 if x is greater than or equal to 0, and returns -1 if x is less than 0. Now, if you're used to math to the signum function, this is not the same as the signum function. It's got a little difference, right? We don't have 0 value for x equal to 0. It's a little different, so be careful there. So let's take a look at an example of how this actually works. So let's say we have 10.4. Then the sign of x is plus, right? So the sign of x is going to be 1. Now, absolute of x plus 0.5 will be 10.9. We get 10.4 plus 0.5. The integer value of that is 10. And if we multiply sign of x, which will be 1, since we have a positive, times this, we get 10. So, 10.4 got rounded down to 10. Now let's look at 10.5. Now 10.5, we expect, when we're rounding away from 0, that it's going to go up to the next number. So it's going to go up to 11, right? Because we have a tie, and so we're going to go away from 0. Again, the sign is positive, so it will be a value of 1. The absolute value here of x is still 10.5, plus 0.5, we get 1. If we truncate that, we get 11. Multiply that by 1, we get 11. So we have the right result. Let's look at 10.6. Well, the same thing, it's positive, so the sign will be 1. The absolute value is 11, that 10.6 plus 0.5 is 11.1. We truncate it, multiply by 1, we get 11. Everything works good so far, but these were positive numbers. Now we need to also make sure that it works for negative numbers. So negative 10.4, that's a negative, so the sign is going to be -1. The absolute value, well, it's going to be 10.4 plus 0.5, so 10.9. And now we get, when we truncate, we get 10. We multiply that now by the -1, and we get -10. So that works. Negative 10.4 rounded to -10. It rounded away from 0. Let's look at negative 10.5, which is the tie. Again, it's a negative value, so we'll have -1 for the sign. The absolute value plus 0.5 is 11. When we truncate that, we get 11, and we multiply that by -1 to get our result, which is -11. Again, that worked. The tie breaking rounded away from 0. That's what we wanted. With negative 10.6, it should just round to the closest, just like negative 10.4 or 10.4 and 10.6. Right? It's only for ties that we have to decide whether we go away from 0 or not. So negative 10.6 is negative. We do the calculation, 11, and we end up with -11. So this works, right? Negative 10.4 rounded to -10, negative 10.5 to -11, negative 10.6 to -11, and positives worked as well. Now I do want to point out that this formula here is also the same thing as doing this, as taking the sign of x, multiplying that by 0.5 and adding that to x. Basically we're saying, do we want to add or remove 0.5 from the value before we truncate? That's equivalent, and so this might be a little easier to code. Here we only have a single kind of special function called sign, whereas here we have the sign and the absolute value, so a little more efficient. Now, Python doesn't have a sign function, but it does have a function in the math module called copy sign. Now, how does the copy sign work? Well, copy sign takes two parameters, x and y, and it returns the magnitude or the absolute value of x, but with the sign of y. So in other words, if we do sign of x, that's the same thing as saying copy sign of the sign of x and apply it to 1. That will then return either -1 or +1. Right? If x is greater than or equal to 0, the sign here will be 1, so we'll get 1 back. And if it's negative, we'll get a -1 back. So we can use it that way. So let's look at this formula again, which was that original formula we looked at. And we can write this Python code, right? So we have to grab the absolute and the copy sign methods, and then we can just return copy sign 1, x, that will be the sign of x, times the truncation, right, essentially, of the absolute value of x plus 0.5. That will work just fine. But a simpler way to look at it is using this alternative way. And here we can just say int of x plus copy sign 0.5 comma x. So that works the same way, and we'll see that in the code that they're equivalent. It's just a different way of writing it, which is a little simpler. All right, so thanks for watching, and in the next video, we'll jump right into the code. See you in a bit.